Hello. In the previous videos, we were considering the theory behind gravitation. So now in this section, we are going to do the examples. So let's start with the first one. The first one is saying a 50 kg man. A 50 kg man, so the first mass is 50 kgs, and the second mass, so I'm going to call them M1 and M2. 50 kg man and a 70 kg person are sitting on a bench. Estimate the magnitude of the gravitational force each exerts on the other. Assume that G, here we're given the value of G that we're supposed to use. Assume that G is 10 to the power of minus 10 Newton meters squared per kg to the power minus 2. That's what we're told to use. So let's calculate the force of gravity using this. It's easy because we already have the formula. Formula is saying F is equal to G m1 m2 over r squared, r being the distance between them. So now here we're going to assume that the distance between them is equal to 0.5 meters, or just half a meter. They're waiting for a bus together, so we need to know the force of attraction between them. So this is equal to 10 to the power minus 10, because that is our G, and our M1 is 50, our M2 is 70 over our R squared, which is 0.5 squared. Notice one thing. These masses are in kgs, which is what? The SI unit of mass. So this is 50 kgs and 70 kgs, and this R is in meters because that is the SI unit. So these, they have to be in SI units. So with this, punch into your calculator, you get the force up to be approximately 10 to the power minus 6 newtons. That is the force of attraction between these two. Easy, because it's just a matter of substituting. Let's go to example number 2. Example number 2 is saying, what is the force of gravity on a 2000 kg satellite? M is equal to 2000 kgs. 2000 kgs. So it's asking, what is the force of gravity on a 2000 kg spacecraft when it orbits 2 Earth radii from the Earth's center? So the radius of orbit is going to be, let me call big R. The radius of orbit is going to be 2 Earth radii. This is the what? The radius of the Earth. So it's saying when it orbits 2 Earth radii from the Earth center, a distance RE is equal to, we are given that RE is equal to 6380 kilometers above the Earth's surface. Then mass of Earth, we are given that M of E is equal to 5.98 times 10 to the power of 24 kgs. Alright, this is a very interesting situation to me, because I'm seeing that there are methods of calculating this. That the easier method for me is what I'm going to use here. The other method is for you to use the formula, and I'll leave that for you to just do, but I want to emphasize the other part. The first part I've already done here. It's the same as just substituting the values there, but I don't want to do the substitutions. I want to use what Newton discovered. So the spacecraft, we are told that the spacecraft is twice as far from the Earth's center as when it is at the Earth's surface. How do we know that? Because here we are told that it's 2 times Earth radii. So let me draw the Earth like this. The satellite is going to be somewhere here, right? And that's where the satellite is. And we are told, okay, this is not to scale. This looks just way too much. Okay, let me put it here, because we are told that this is, okay, this makes better sense. We are told that it's two times radius of the Earth away from the Earth's center. So there's going to be RE here, and there's going to be another RE here, for it to be 2 Earth radii from the what? From the Earth's center. So spacecraft, since the force of gravity, now we want to calculate the force of gravity, isn't it? We know that from Newton's law of gravitation, the force of gravity decreases as the square of the distance. That's what we know. It decreases with the square of the distance, isn't it? So here, when the satellite is at the Earth's surface, when the satellite is at the Earth's surface, compared to where the satellite is right now, which is 2 times the what? The distance, which is 2 times the distance of radius. Well, actually, yeah, I think I made. Okay, let me continue with the question, just explaining the solution. I think it will just work the same way. Okay, so now it means this force of gravity, since force is proportional to 1 over r squared, the force of gravity at this point, since this is twice from the center, it basically means the force of gravity has decreased by 1 over 2 squared, which is equal to a quarter. It has decreased by a factor of 1 over 4 compared to when it's at the what? At the surface of the earth. I hope that makes sense. It has decreased by 1 over a quarter because of the what? Of the inverse square law, that F is inversely proportional to the square of the radius. So this basically means the force of gravity at this point is equal to the quarter of when it's at the earth's surface. But what is the force of gravity when it's at the earth's surface? When it's at the earth's surface, it is just the weight of the object. So it is a quarter of mg at the earth's surface, g being the acceleration due to gravity at the earth's surface at this point here. So this is equal to a quarter. We have our mass 2000 and we have our g as 9.8. When you do the calculation, this will be 4,900 newtons. So here I used the inverse square law to calculate, because now I know that it's twice the distance. When it's twice the distance, then the force gets quartered, because when it's twice, 1 over 2 squared is a quarter, so the force gets quartered. When it's thrice, the force gets 1 over 9. It will be 1 over 9 factor, because what? Because of the inverse square law. So I hope you managed to follow this example as I was explaining it. That these I do not, which means these I do not need to use. That's what I didn't want to use. I didn't want to use all these calculations, convert this one to SI unit, and then use this formula here. It was just going to be too much work. So I decided to use the other formula that just uses the inverse square law. The other method that uses the inverse square law. That I'm going to compare it with what? With the situation when it's at the Earth's surface. At the Earth's surface, the radius is just going to be r. But I've increased the radius to the radius of orbit now is 2re. Since it's now 2re, compared to the situation where it's just re, the force at this point now is just 1 over 2 squared of the force when it's here. And the force at this point is the mg. So it's 1 over 2 squared of when it's mg. So that is the reasoning behind this. So you get your 4,900 newtons. Okay, let's move on to another example. It's example 3. It's saying, find the net force on the moon. Mass of the moon, I'm going to call it mm, mass of moon, is equal to 7.35 times 10 to the power of 22 kgs. So it's saying, find the net force on the moon due to the gravitational attraction of both the Earth and the Sun, assuming they are at right angles to each other. Doesn't that sound fun? Let's do that one. We are given that the mass of Earth, I'm going to call it mass of Earth, ME, is equal to, we are given that it's 5.9 times 10 to the power of 24 kgs. And we are given that the mass of the Sun is equal to 1.99 times 10 to the power of 30 kgs. Isn't it? That's what we are given. So here we are told that they are at right angles to each other, and we want to find the overall effect of the mass on the moon. So let me figure out what is happening here. Imagine the moon is here, and I would recommend you guys draw what do you call this? Draw diagrams to just get a feel of what is going on. I'm told that they are at right angles to each other, isn't it? So something like that. That's what I'm told. I'm told that it's going to be it's something like that. It's something like this. Because they are now at what? They are at right angles to each other. Let's see. Will this work easier? Okay, okay, wait, I'm just going to get something. Okay, let me write them the other way around. Let me write them the other way around for it to be easier to calculate. Let me just rub this off so that it becomes easier for me to calculate this without changing much. I'm sorry, my papers are getting a bit dirty. I'll have to wash them in the morning. Right now I think it's around 2:30 a.m. So there's no point in washing them now. I'll wash them in the morning and put them in the sun to dry. So imagine the moon is here. So our M of moon is there. And imagine our earth is here. So our M of earth is there. And imagine our sun is here. So our M of S is there. So it's going to be like something like this. Not drawn to scale at all. It's not drawn to scale at all. So it's actually something like this. This line, we do not need this line because we are not considering the relationship between sun and earth. We just want the relationship between the moon and the earth, and the relationship between the moon and the sun. So which means this earth will pull the moon with a force equal to F force of earth on sun on moon. I mean force of earth on moon. It's going to pull the moon to this side. You understand? And this sun here is going to pull this moon with a force Fs moon, force of sun on moon, and it's going to pull it down. And as you know, if forces are pulling in these directions, it means the overall effect will be somewhere in between the two, like this. That is the overall effect, which is the resultant. So this is the resultant that we want to get, because they said what the overall effect of the what of those forces. So let's calculate FEM. FEM is just calculated using the formula G, the mass of the two bodies that are in the question. Since we're calculating EM, is the mass of the earth and the mass of the moon all over our distance of the, let me call it earth moon. So this is distance. RE is just distance of earth to moon squared. For what? For us not to confuse when we're doing the distance of the sun. So this is mass of earth, mass of moon over distance of earth to moon squared. Let's put the figures in. Let's put the figures in. This is equal to, that is equal to G, which is 6.67 times 10 to the power minus 11, mass of earth, which is 7.35 times 10 to the power of 22, and then mass of moon, which is 5.98 times 10 to the power of 24. All divided by what? By the REM, the distance from the moon center to the Earth's center. That is the REM. So this is REM. So REM squared. I think I didn't state the distance. We're given the distance as 3.84 times 10 to the power of 8 meters. So this one is going to be squared. Putting that in the calculator, you get 1.99 times 10 to the power of 20 newtons. So this FEM here is 1.99 times 10 to the power of 20 newtons. Listen. So now let's calculate FSM. We are going to do it the same way. FSM is calculated as G. The first mass concerned is the mass of the sun. The second mass concerned is the mass of the moon over the distance RSM squared. RSM being the distance between the center of the moon and the center of the sun. So this one is RSM. So that's what we are going to consider now. So now let's do that. Putting the respective values, this one will be 6.67 times 10 to the power of minus 11 multiplied by 7.35 times 10 to the power of 22 multiplied by 1.99 times 10 to the power of 30 times 10 to the power of 30 all over 1.50 times 10 to the power of 11, and this is going to be squared. Here I just mixed the masses. This is the mass of the sun, and this is the mass of the moon. So I just swapped them. I think I did the same when I was doing the force of the earth on the moon. I swapped them from the convention, from the where I had written them on top there. So this one will give you approximately 4.77 times 10 to the power of 20 newtons. So using a diagram, we have our force here, which is 1.99 times 10 to the power of 20 due to the earth, and our force here, which is 4.77 times 10 to the power of 20 newtons due to the sun. Now it's just a matter of getting the resultant force, and the resultant force here we can use Pythagoras, because we can transpose this from this part and put it here. Now we have a right angle triangle. When we have a right angle triangle, this one becomes the hypotenuse, and we can calculate that using Pythagoras because it's a hypotenuse. So FR will give you a force of 4.77 times 10 to the power of 20 when you apply Pythagoras theorem. That is what? The force, that is the overall force of these two, of the effect of the presence of the earth and the what? And the sun. The overall force on what? On the moon. And we can get theta, we can get angle theta with respect to the direction of the sun. Theta will be equal to arctan of 1.99, which is the opposite side, since it's equal like this, 1.99 times 10 to the power of 20 all over the adjacent side, which is 4.77 times 10 to the power of 20. When you punch this in a calculator, you get 24.6 degrees. So it will be, so the force, the overall force is 4.77 times 10 to the power of 20 at a direction 24.6 degrees to what? To the direction of the sun. That is the third example. In the next section, we are going to move to another part where we are considering close to the earth, and then we are going to move into satellites. So stay tuned for that video.